Natural physics is a concept astrophysicist Leroy Larry developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as Leroy's astrophysics doctoral research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
Greetings, I'm Leroy Larry and welcome to the Natural Physics Experience, live from Costa Rica. What made the Hulk the Hulk? Gamma rays. Gamma rays are the most powerful form of energy known to exist in nature. More powerful than radio waves, microwaves, infrared, optical, ultraviolet, and X-rays. Gamma rays are at the extreme end of the electromagnetic spectrum. Gamma rays come from cosmic rays. Cosmic rays were first discovered in the 1920s, and no one knows where cosmic rays come from.
Has anybody here ever seen the movie Predator? Good movie from the 80s. The alien wore a helmet which allowed it to see in different wavelengths of light: optical, X-ray, infrared, ultraviolet. We may not have a helmet like the Predator, but we do have ground-based telescopes and space telescopes orbiting high above the Earth's obscuring atmosphere, which do allow us to look into outer space with different eyes that enable us to see in the different wavelengths of light. The visible range in which we see is a small part of the electromagnetic spectrum. Just as a group of 6 runners clasping arms will break apart when running from the beach into the ocean, a beam of light breaks up into the 6 major colors of red, orange, yellow, green, blue, and violet, because these colors travel at different velocities when traveling from one medium into another. A new image from NASA's Fermi Space Telescope shows gamma rays, the highest energy form of light, filling faraway bubbles of hot gas created by massive stars. The bubbles are located about 4,500 light years away in a star-forming region of the constellation Cygnus, the Swan, also dubbed Cygnus X. The outflow from Cygnus X's gigantic stars also creates intense magnetic fields within the bubbles, and it is these magnetic fields that help spawn the gamma rays by trapping and deflecting fast-moving particles called cosmic rays. Cosmic rays are tiny electrically charged particles that move at nearly the speed of light. They are primarily protons, and most were probably accelerated to their incredible speeds by star explosions known as supernovas. When cosmic rays collide with interstellar gas, or photons of starlight, they give off gamma rays. Here on Earth, we have particle accelerators that can produce high-energy protons. The largest in the United States is the Fermilab Tevatron, with a circumference of 6.86 kilometers, capable of producing protons with energies of 1 trillion electron volts, TeV. The largest in the world is the CERN Large Hadron Collider, LHC, with a circumference of 27 kilometers, capable of producing protons with energies of 13 trillion electron volts. However, cosmic ray protons reach us with energies thousands of times greater. The solar wind streams off of the sun in all directions at speeds of about 400 kilometers per second. The source of the solar wind is the sun's hot corona. The temperature of the corona is so high that the sun's gravity cannot hold on to it. This image, dated September 18, 2003, is from the SOHO Extreme Ultraviolet Imaging Telescope. The sun's atmosphere is threaded with magnetic fields, indicated by the yellow lines. Areas with closed magnetic fields give rise to slow, dense solar wind, indicated by the short, dashed red arrows, while areas with open magnetic fields, so-called coronal holes, yield fast, less dense solar wind streams, indicated by the longer, solid red arrows. In addition to the permanent coronal holes at the sun's poles, coronal holes can sometimes occur closer to the sun's equator, as shown here just right of center. The solar wind is a stream of charged particles released from the upper atmosphere of the sun. This plasma consists of mostly electrons, protons, and alpha particles with energies usually between 1.5 and 10,000 electron volts, keV. Embedded in the solar wind plasma is the interplanetary magnetic field. The solar wind varies in density, temperature, and speed over time and over solar longitude. Its particles can escape the sun's gravity because of their high energy, from the high temperature of the corona, and magnetic, electrical, and electromagnetic phenomena in it. The solar winds flow outward supersonically at varying speeds depending on their origin, reaching up to around 2 million kilometers per hour to great distances, filling a region known as the heliosphere, an enormous bubble-like volume surrounded by the interstellar medium. Streaming out of our nearest star at speeds of 400 to 760 kilometers per second, the solar wind strips planets with no magnetic fields and shapes the magnetosphere of those that do. In the case of the Earth, these highly charged particles are deflected by the Lorentz force and shaped into a long comet-like tail whose boundary is called the magnetopause. Geomagnetic storms can affect power grids, reroute high-latitude air flights, cause errors of up to 46 meters in global positioning systems, interfere with satellite communications, and endanger space missions and their crews. This is the Northern Lights, or Aurora Borealis. The aurora is caused by particles from the sun, the solar wind, which are trapped in the magnetic field of the Earth and then into the atmosphere, causing light. This is data from the Galileo space probe. This is a view of the plasmasphere surrounding Jupiter that we obtained through the eyes of the plasma wave instrument on board the probe. The colors represent energy levels, and this data shows the change in energy as time goes by. A long time ago, in a galaxy far, far away, I was in the Boy Scouts. We went camping far away from the city lights, and I remember looking up at the Milky Way. It really did look like milk had been spilled across the night sky. I did not know it then, but I was looking along the galactic plane towards the center of our Milky Way galaxy. This is a view of the galactic plane of our Milky Way galaxy in the optical range of the electromagnetic spectrum. These are views of our galactic plane in the radio, microwave, infrared, ultraviolet, X-ray, and gamma ray wavelengths of the electromagnetic spectrum. This is data from my research using the eyes of the Fermi Gamma Ray Space Telescope. Our galactic plane is divided into 86 regions to detect as yet undiscovered gamma ray sources. Software programs are used to analyze and model the data. Here are indicated two hotspots, locations of potential new gamma ray sources.
This is the actual glossy photo that was printed out in the laboratory at the NASA Jet Propulsion Laboratory. Data that I received back from Galileo at Jupiter after I had sent commands to Galileo. Traveling at the speed of light, which is 186,000 miles per second, not per hour, per second, it took my commands 45 minutes to get to Galileo, and then another 45 minutes to receive this data back here on Earth. And I always got such a kick out of the fact that my name had traveled through interplanetary space, right? From Earth to Jupiter and from Earth to Jupiter. How cool is that? Here are the commands that I sent to Galileo to get that data back that you see in the glossy printout. And there you can see Leroy, GLL stands for Galileo, and you can see the year is 1996. And then here's commands that went to the plasma instruments that were on board Galileo. That is dated May 24th, 1996. This is what my wife Tears and I call a cool creepy. Because it's very cool, but it's a little creepy in a good way. 5/24 is the birthday of my wife. So in 1996, I sent a command to Jupiter to get data back on the birth date of my future wife. How cool is that?
Cosmic rays are high-energy protons, ions, and electrons that astrophysicists believe are produced when a star explodes into a supernova. As the shock wave from the explosion expands out into space, it encounters protons, ions, and electrons. Its magnetic field pushes them up to very high speeds, and they gain energy by repeatedly crossing the shock. The process, called diffusive shock acceleration, or DSA, is thought to be facilitated by scattering off magnetic turbulences downstream and irregularities upstream. Charged particles change trajectories when they encounter a magnetic field, making it impossible to directly determine where cosmic rays come from. The source of gamma rays are traceable because photons have no charge and are unaffected by a magnetic field. Cosmic rays can reach energies up to 10 to the 21st electron volts, and below 10 to the 15th electron volts are thought to be of galactic origin. The most promising sources of galactic cosmic rays are supernova remnants, or SNRs. They are not only energetically favorable, but also provide a mechanism to accelerate particles to very high energies. An important window of observations in the range from 100 mega to 300 giga electron volts has been opened with the launch of the Fermi Observatory. Much of the gamma ray emission can be explained by Bremsstrahlung emission and inverse Compton scattering. However, the model cannot fit a distinct feature at giga electron volt energies, which can be accounted for by adding a pion component to the model, providing evidence for cosmic ray production. Despite all the findings that link SNRs with high-energy electrons, direct evidence for the acceleration of ions by these objects is still lacking. In order to find a signature for proton acceleration, studying the photon spectrum of the sources at gamma-ray energies becomes fundamental. It is expected that a fraction of the high-energy emission would be caused by the decay of neutral pions produced through collisions of accelerated protons with cold ambient protons and ions. If the astrophysicists can prove that the accelerated protons are producing the gamma rays, then the mystery of cosmic rays will be solved.
Think of a page full of signatures, and you're looking for that one signature that will point to the origin of cosmic rays. Everyone, tune in next week. Same fat time, fat physics with attitude, same fat channel.